Hello. I'm starting chapter 2 on set theory, and I will cover the first section. So chapter 2 is set theory. The first section that I'm covering in this video is the language of sets. Okay, so a set is one of those things that are hard to define in math, but we can think of a set as a collection of objects. So a set can be thought of as a collection of individual objects called the elements or members of the sets. Of the set. Okay, so that's a rough idea of what a set is, and we can represent a set in two ways. We can write a set by either listing its elements within braces, or by using set builder notation. Okay, so let's show a couple of examples of listing the elements of a set within braces. Okay, the first set is the set of US Armed Forces. Okay, so there are two. I mean, this set has 4 elements. We can denote the set with the letter A. And by listing the elements within braces, the set of US Armed Forces, the elements of this set are the Army, the Navy, the Air Force, and the Marine Corps. And that's it. You're thinking of the Coast Guard. Well, that's not considered that's not considered an element of this set because they belong to a different department. So these 4 are part of the Secretary of Defense, and the U.S. Coast Guard is part of the Secretary of Homeland Security. So for that reason, I'm not including the Coast Guard. Another example is the set of integers between 1 and 100. So if we include the first and last value, the elements are going to be, well, this is going to be very long to write one by one. What we can do is write an ellipsis or 3 consecutive dots to indicate that the pattern continues. So write the first few elements and write the last one, or some of the last one. Okay, so this one way to write sets, by listing the elements within braces. But sometimes that's not going to be the most convenient way to write a set. So another way is using set builder notation. So if the elements of a set all share some common characteristics that are satisfied by no other object, we can use set builder notation to represent the set. And they give you this example with the set of carnivorous animals. Okay, sometimes it is not convenient to use braces. And if the elements of a set share some common characteristics, we can use them. We can use set builder notation. So one example, I'm going to use the same example as in the book. The set of all carnivorous animals. Okay, so we can denote this set with the letter C. So in set builder notation is going to look like this. We're still going to use braces, but that's going to be the set of all X. We're going to use a bar, or the book is using a column, so I'm going to use that, such that X is a carnivorous animal. So this read, that column means such that. And this reads the set of all X such that X is a carnivorous animal. Okay, the next example is very important. And actually, in chapter 6, we're going to spend one section for each set. So this page 44. This example is on page 44. We're going to briefly describe each of the following sets of numbers. Okay, the first set is the set of natural numbers. So the natural numbers are the counting numbers. We can denote the set with the letter N. So the counting numbers, well, the first element is going to be 1. It's not going to have a last. It is not going to have a last element. So we can just indicate. We can write the first few elements and then indicate a pattern with an ellipsis with 3 dots. B, the set of whole numbers. So the set of whole numbers is going to be the set with the natural numbers and the number 0. Make this a little bit bigger. So the set of whole numbers is going to be the natural numbers and the 0. And the set of integers is going to be the set of the whole numbers and the opposites of the natural numbers. So we can denote this with the letter I, or sometimes that's written with the letter Z. And this one is not going to have, the first two had a first element, but didn't have a last element. This is not going to have either a first element or a last element. So we can use the ellipsis in the middle, at the end, or at the beginning. So we need to use 2 of those at the beginning, then indicate the pattern, and this pattern will continue. Okay, part D is a set of rational numbers. Okay, so let's write this down. The rational numbers That's going to be the fractions of integers. So we can denote this with the letter Q. We use the letter Q for quotient. So that's going to be the set of all x such that x can be written in the form A over B. Where A and B are integers and B is not zero. Or what we know as the fractions, the set of fractions. And the name rational comes from ratio. So they are called rationals because they are going to be the ratio. They are going to be ratios of two integers. Okay, so yeah, so it looks like this whiteboard froze. So I'll have to close it and open it again. So let's open this whiteboard again. And I'll get back. Okay, so back to where we were. Okay, so the set of the set of rational numbers, the name rational comes from a ratio, and that's going to be essentially the fractions. So some examples of rational numbers. Now that one is going to be hard to list the elements one by one. That's why I use a different notation. But it's going to be hard to establish a pattern. So it's better to use a different notation. So some numbers can be 3 over 5 or 6 over negative 11 or negative 7 over negative 8 or negative 4 over 3. And you can see integers as rational numbers with denominator 0. So another could be 5 because 5 is the same as 5 over 1. And the last one is the set of natural numbers. I'm sorry, it's the set of real numbers. So I'm not going to go into details with this one. I'm just going to tell you that the set of real numbers yeah, I'm not going to give you any more details. We're going to see the sets with detail in chapter 6. We're going to spend one section on each set of numbers. But you can write this as R. We can denote the set of real numbers as R, and that's going to be the set of all x, such that x has a decimal expansion. And later, in chapter 6, I will explain this with more detail. Or you can also think of the set of real numbers as the set of all numbers that can be represented on a number line. Okay, so these sets are important. So now in example 2, they give us a set either by listing the elements within braces, or in set builder notation. What we are going to do is write each set the other way. Like A, we're going to write in set builder notation, and B and C, we're going to write the set by listing the elements within braces. This, by the way, on page 44. Okay, so in A, we're going to use set builder notation. Okay, so set T is going to be the set of all X such that X is a block type. And B and C are written, sets in parts B and C are written in a set builder notation. We're going to write this the other way, in an alternative way. So set B is the set of all Y, such that Y is a color of the American flag. So we can list this as red, white, and blue. So I wrote them in this order for no particular reason, but I could have written as blue, red, and white, or white, blue, and red. We'll see in the next section, we'll see that the order in which we write the elements is not important. So you can write, you can change the order, or you can repeat elements, and it's the same set. And part C, A is the set of it's the set of all A, such that A is a counting number or a natural number less than 20, and is evenly divisible by 3. Okay, a counting number, the first counting number is 1. 1 and 2 are not divisible by 3, but 3 is divisible by 3. Then 4, 5 are not divisible by 3, so the next one is 6. Then 9, 12, 15, and 18. The next one is 21, but that one is greater than 20, so that's not part of the set. Okay, so I'm going to copy the next definition and example. When is a set well defined? This on the next page, page 45. A set is well defined if we are able to tell whether any particular object is an element of that set. So they are asking us which sets are well defined. The first set is the set of all X, such that X is a winner of the Academy Award. And this one is well defined because you can name an actor, or you can name a celebrity and tell whether the actor won an Academy Award. So give me the name of an actor like Ryan Reynolds. We know that this, well, or we can look at a database and find that he's not an element of this set. Or another celebrity or another actor like let's say Leonardo DiCaprio. He's an element of that set. So the set is well defined. So in A, the set in part A is well defined. So for example, let's say Eminem is an element of the set. And Kanye West is not an element of the set. Now, in B, the set is the set of all x, or the set T is the set of all x, such that x is tall. Now, that one is not well defined. The set T is not well defined. And the problem is that we don't know what they mean by tall person. Is it somebody 6 feet or taller, or 6'2" feet or taller? It doesn't say clearly. Like somebody that is, let's say, someone that is 6'2" feet tall might be taller than the average American, or maybe taller than average. But if we compare that person with a group of NBA players, the person is not going to look tall. It's going to be shorter than most. So this is not well defined because there is no clear interpretation of tall. Okay, we have a couple of special sets that we use mainly for reference. We're going to see operations in the next two sections, operations with sets. But two special sets are the empty set and the universal set. Okay, so we're doing first the empty set. And the empty set is that, the set that is empty or that contains no elements. This page 46. So that's page 46. The set that contains no elements is called the empty set or the null set. That is labeled by the symbol with a circle and a line crossing it, or another notation is the empty braces. But most of the time we're going to be using the first symbol. So the notation for the empty set is going to be this. We're not going to be using the empty braces. Okay, so we saw when we did the problem solving techniques, we saw the splitting hairs principle. If two things look if two things look similar but are slightly different, they don't mean the same thing. So they are asking us whether the set containing the empty set have the same meaning as the empty set. And the answer is no. Actually, I'm just going to read this. I'm just going to read the explanation. So note that the set containing the empty set is not the same as the empty set. To make this more clear, you may think of a set as a paper bag that you might get at a supermarket. Then empty set corresponds to an empty bag. So something that has no elements. Whereas the set containing the empty set is no longer empty. Could be visualized as a one containing a second bag which is empty. Okay, so first set. So do they mean the same thing? The answer is no. Because the set containing the empty set is no longer empty. And B, Do the set containing the empty set and the set containing 0 mean the same thing? Again, the answer is no. They are completely different things. This is a set, and the number 0 is a number. We actually mentioned that example when we did the problem solving techniques, when we did the splitting hairs principle. And the other set is the universal set. That's also on page 46. The universal set is the set of all elements under consideration in a given discussion. We often denote the universal set by the capital letter 46. So universal doesn't mean the set of all things known and unknown. That's just a reference. That's the set of elements that we're considering or all elements that we are working with. So for example, in a certain problem, we may want to use only the counting numbers from 1 to 10. For this discussion, the universal set would be the set of integers from 1 through 10. In another situation, we might consider only female consumers living in the United States. In this case, that is going to be the universal set. Okay, so we have been talking about sets, and we're going to use the element symbol to determine or to indicate whether something is an element of a set or not. So we use the symbol that looks like a knee to stand the phrase "is an element of." Although this looks somewhat like letter E, these two symbols are not the same. Again, the splitting hairs principle. The notation 3 is element of A expresses that 3 is an element of the set A. If 3 is not an element of A, we are going to cross that symbol. Okay, so this symbol is the element symbol. It's going to be the symbol, and stands for is an element of. So if we cross it, that means that something is not an element of a set. So that stands for is not an element of. Okay, so I'm going to copy an example from page 47, the quiz yourself. Okay, so we're going to decide whether each statement is true or false. In A, we have, want to make sure I'm sharing. We're going to decide whether each element is true or false. So part A, 3 is an element of all x, such that x is an odd counting number. So this one is true because the odd counting numbers are going to be 1, 3, 5, 7, and so on. So this one is true. B, 2 is not an element of the empty set. Well, since the empty set has no elements, 2 cannot be an element of something that has no elements. So this is also true. And C, chocolate is the set of all X such that X is a vitamin. This one is false. Chocolate contains vitamins, but it's not a vitamin itself. By vitamins, we understand things like vitamin A, B1, B2, B6, C, K, E, and so on. And chocolate is not a vitamin. Okay, the last thing in this section is the cardinal number to indicate the elements of a set. So in solving set theory problems, we often need to know the number of elements in a set. And that is going to be denoted by N of A. The number of elements in set A is called the cardinal number of set A and is denoted by N of A. A set is finite if its cardinal number is a whole number. An infinite set is one that is not finite. Okay, so let's look at example 5. I'm just going to read example 5. I think I passed this. Oh, yes, there it is. Well, actually, I didn't read example 6, example 5, but that's with elements. So they're asking us to replace the symbol in each element by either is an element of or is not an element of. So in A, 3 is going to be an element of this set. In 5, or in B, the set containing 5 is not an element of the set 2, 3, 4, 5, because 5 is a number and is not the same as the set containing 5, which is a set. In E, or in part C, we're going to use the symbol is an element of, because Bill Gates is an element of the set of billionaires. Also, jogging is an aerobic exercise, so we're going to use the symbol is an element of. And in E, well, the face cards are kings, queens, and jokers. So aces are not face cards. And the ace of hearts is not an element of the set of face cards. But now I'm going to do example 6, which has to do with the cardinal number. We are now on page 48, example 6. State whether each set is finite or infinite. If it is finite, state its cardinal number using N of A notation. Okay, set P. Set P is a set of all X, such that X is a planet in our solar system. There are 8 planets in the solar system, so the number of elements of P is 8. And this set is infinite. The set of natural numbers is an infinite set. C. Set A is the set of all Y, such that Y is a person living in the United States who is not a citizen. So this set is finite, but we don't know the number of elements. This is finite, but we don't know N of A. D, the empty set has no elements. This is a finite set. This is a finite set, and the number of elements of the empty set, if the empty set has no elements, the number of elements is 0. And in part D, each element of this set, each element of the set is a set. So 1 to 3 is one element, or the set containing 1 to 3 is one element. The set containing 1, 4, 5 is an element, and the set containing 3 is also an element. So this is finite, and the number of elements of X is 3. So I'm just going to indicate this is finite. So P, the empty set, and X are all finite sets. So this finishes the first section, section 2.1, and I'm going to stop the video here. So thank you for listening.